Always, I'll open the floor for questions. You know what the test is on, obviously. Exponential work and decay. Exponential growth and decay. And we're talking about logarithm. Anybody hot? Are we hot or cold right now? Very hot. Just a little neutral. You're in a neutral state. I'm pretty okay. I'm in between. I was in the math science office and the air is like pumping and the doors closed, so I'm not a big fan of super cold. But a big room, I can do that.
Also, I think it's worse when you're sitting down. I feel it's like more warm when sitting down.
Do you?
Standing up,
I wouldn't live with that moving when you're standing up and you more warm.
but you're not. You're just standing up. There's sometimes like just standing there is makes me.
It's because of your left.
You just kind of walking.
I guess I do move.
You're just standing like you're not. You're receiving it.
All right, exponential growth, decay, and logarithms. So, yeah, John.
I have a question.
Yeah, good.
It's actually a graphing question.
Okay, what's the equation, the function?
F of x equals log base 3. Parentheses x plus 4 minus 2.
Okay. So we got log base 3 of x plus 4 minus 2. Great example to start us off with. Pretty much at this point, you know what you're going to have. You're going to have a graph on logs for sure, and a graph on growth or decay. Maybe one of each, but definitely a graph at least, at a minimum, one of the growth, decay, maybe one of each. But you have to be able to do this every time. When you think of the log graph, what I started telling you was, hey, think of the exponential growth graph for this. So think of y equals 3 to the x. So whatever the base is right here, I want you to think of that as the base of a growth or decay graph. And then I want you to come up with the main 3 points for the growth or decay, and then do what with those 3 points? Why are we switching that? Why are we switching the 3 points?
Because when you switch them, that's how you get the standard graph.
That's how we get, in this case, it would be the inverse of the exponential, which is the log graph. The log graph, which is what we're looking for. Logs and exponentials are inverses of one another.
Are the equations for like half-life and stuff going to be able to test or should we memorize those? Because like each for the.
Let me finish this problem. I think you have a question about this problem. It's still in the middle of the problem, right? Give me 1 second. I'm glad you're excited about that. But no, they're not going to be there. But you need to have the main ones down pat. The first 2 you should know. So if we think about y equals 3 to the x, and we look at our xy table for these points, we start as always with negative 1, 0, and 1. And then we come up with the y values from those. They're always going to be b, which is this. Remember, this will always be the b value, which is the base itself. This will always be 1 over b. So that'll be 1/3. And the middle value will always be 1. And check it if you don't believe me. Try these 3 x values in this equation, and these are the 3 values that you will get as a result. Now switch x and y and make a new log table on the left. So my log table will be read as this. So there's my y values that now become the x. And here are my x values that now become the y. Am I done though? Can I stop there?
No.
Why not, David? What else do I have to do so?
Well, yeah. The y. We already copied the y new, x new.
Very good. Exactly. So we have to do our transformations. In this case, those transformations happen to be translations. The graph is slid left to right or slid up and down. So as a result, we have to consider that. So I know already that when I see a minus 2 on the end, I'm going to take 2 away from the y values because this is always my vertical shift. Why am I not multiplying the y values by any number? Because in the class we've done this a couple times, right? I first multiply the y value, and then I take into account the vertical shift. Why, Gus, am I not multiplying by anything?
Because there's no constant in front of the log.
What's really in front of this log right now, everybody? A 1. And what's 1 times these numbers? These numbers themselves. Very good. So instead, to get the new y value, all we have to do is subtract 2 from everything. So let's write it down if it helps. I'm going to write it for today. I'm subtracting 2 from each of those. So that becomes a negative 3, that becomes a negative 2, and that becomes a negative 1. Again, that's because of this negative 2 that we're seeing over here on the right. That negative 2 is what tells me to drop 2 from each y coordinate. And then with x and h, who could tell me what happens with that? With this here? This plus 4, what's happening? Yeah, why am I subtracting 4 from each of these x's? Go ahead, Lo.
Because it's like h minus k, so you know it's gonna be a minus, and because that gives you positive.
So it's x minus h. So we have to consider the fact that if we have x minus h, we have to do the opposite of what we're seeing there. So again, this is the x minus h plus k on the end. So we always do the opposite of what happens to the horizontal translation and whatever happens to the new or the vertical translation. Now you could also have problems, by the way, with the number here, but I haven't gotten into that, so I'm not going to introduce that just on the test. But that would be a horizontal multiplication. You have to multiply x, just like we multiply y if there's a number outside here. I'm not going to get into that right now because it's new. So let's subtract 4 from all of those x values. 3 minus 4 is negative 1. 1 minus 4 is negative 3. And then 1/3 minus 4 is negative 3 2/3. So again, I'm taking the x coordinates and subtracting 4, subtracting 4, subtracting 4 from each of those values. Okay, from each of those.
What would happen if there was 2 log 3 and the rest of
Like a 2 here?
it? Yeah.
So you would have had to double these first and then subtract 2. And it's the same process with exponential growth over there. John, if I put a 2 in front of here, then I would take the y values and double them first, and then if there was like a plus 7, and then I would add 7. If the exponent had a minus 6, I would add 6 to all the x's. So it's the exact same process in both cases. It's coming up with the coordinates that's most important, and then obviously at the end, recognizing the general shape of these graphs. So if I look at my coordinates alone, just look at my coordinates, people. I'm clearly going to be negative x, negative y. So what quadrant is that mainly going to be in? Try it.
Bottom right.
Bottom left.
Bottom, wait. Yeah, bottom left.
Yeah.
And that's, I was thinking because it flipped, but bottom left, I don't know.
Third.
Right?
It's 1, 2, 3, 4 in the shape of a letter C. I don't think of it that way. 1, 2, 3, 4. You always make letter C. Calculus, calculator, whatever you want to think of to remember
If
that.
there was before the log 3, like 3 times, then the y finally can multiply 3 times all the y new values.
This gets multiplied first, make a PEMDAS. Do the multiplication first, and then do the subtraction or addition at the end. See what I'm saying? So triple these numbers first, neighbor, and then subtract 2. Okay? That's a great question. Do you remember, with exponential growth and decay, we have a horizontal asymptote over here on the right. I'll jot it down. And it's always equal to y equals, in this case, k. Here, there's going to be a horizontal asymptote, and it's always x equals, it's not k, it's h. So in this case, the h value would be negative 4. So we go back 4 units and put in our vertical asymptote.
It's negative 4, okay?
Because h is negative 4, right? Think about what h was. H was its minus 4 we took off from all the x's. So that is the graph of x equals negative 4. Or the graph, the boundary. So what does that help me? Why does that help me? Yeah.
Helps find the shape.
Good. The general shape of a log graph looks like this. Right? Okay, that's literally what it looks like. That's the log shape. You should know that by now. Now, if I had a negative in front of the log, this going up would be now coming down. This continuing up would continue down. So this is a log graph. This is a negative log graph. I literally take what's down here and flip it over the x-axis. Take what's up here and flip it over the x-axis. So that's if there's a negative in front, the whole shape would look like this then. But you would also see it from your coordinates. So let's plot our coordinates, John.
When you say domain and range, is that what you apply x and y?
Well, in this case, the domain is x values greater than or equal to -4. How do I know that? Because this is an asymptote, right? So it's going to start along it, and it's going to ride along, and then it's going to continue everywhere to the right. So that's the domain. The range is all real numbers. The range is always all real numbers for log, and the domain is always all real numbers for exponential. So for these graphs, they differ in their range and domain. They kind of switch because they are what of each other? Inverses. It is just greater than. I don't know why I wrote equal to. I just realized that as you're asking it too. Thank you. Yeah, it's definitely not greater than or equal to. It is just greater than because -4 cannot be reached. It's a vertical asymptote. Thanks, Altea, for mentioning that. So our coordinates, again, are going to be what are circled in red. Okay, what are circled in red, those are our coordinates. We got x, comma, y, x, comma, y, x, comma, y. So it's really pretty much -3, -3 to start. Close enough. Again, for these, you know, I told you already, once you get the coordinates right, I'll be happy with that. Your graph should be generally right. You're going to estimate some of the coordinates, like -3 and 2/3. That's just really close to -4, right? Over here. And then down to -3. So there's my first coordinate right there. My second coordinate is at -3, comma, -2, which is right there. And my third coordinate is -1, -1, which is, oops, sorry, -3, yeah, -3, -2 is right. So when I look at this graph, I can see the curvature, I can see what's happening already. It's going to ride along the asymptote and then curl in that direction. What's another point that I said could be useful if you really wanted to have one more point? Yeah, an x-intercept, if you wanted to. I'm not going to be a stickler, though. So when it comes to doing work, if you don't need to do it, why do more? So that works for me. Okay? It's a general shape of what the graph looks like. I know it's going to cross at some point because this graph ends up going up and to the right forever, which is why the range is all numbers because this goes down forever and this goes up forever. The domain is only to the right of this because it's going to go to the right forever. That's what the domain and range are what they are. Again, not to confuse the two, and put a line between them. I could very likely ask you, graph the exponential and then graph the logarithm of inverses and see that they're inverses in the same graph. You could graph this function and then it's inverse at the same moment and just see that you get that. If you do have inverses on the graph, what should they exhibit? Sean?
Symmetry plus the line y equals x.
Symmetry over the line y equals x. Remember, inverses exhibit symmetry over the line y equals x. So let me graph the line y equals x to show that. Here's what it looks like. Close enough. There's the line y equals x, or close to it. So if this were the exponential function that shows the inverse of it, ready? Watch what I would do to create this. Some of you are still in trouble, I think, with visualizing. Watch what I'm going to do. I'm going to take this graph and reflect it over the line y equals x. See what I did there? I'm going to take this piece that curls off that way and curl off that way. So continuing the blue line curled off at about the same curvature as the black line on the other side of it. See how these are now symmetric over that line, symmetric, and then here what's going to happen, the same thing, is that this is going to curl like that. And what's my asymptote going to be now? X equals, y equals -4 instead. So this graph will curl, or in this case -3, sorry, -3, -3. And that would be the horizontal asymptote, the exponential graph. So those are clearly inverse of each other. You can tell, tilt your head. It's not obvious, just tilt your head to the side. Look at the line, look at this line as a vertical line, and you'll see the symmetry on both sides. John.
So can the inverse of a logarithm function cross the vertical asymptote?
Well, the vertical asymptote isn't for that function, so yes.
Can cross it.
Because the vertical asymptote is only for the log function. It's not for its inverse. The minute you graph the inverse, the asymptote doesn't apply to it anymore. Now the horizontal asymptote applies to it. Yeah, good question. Nick.
So
when you're doing the inverse of a log, you just don't have to switch y and x originally, and you do the same thing.
If you're finding the inverse of a log function to get back to the original exponential, you would switch x and y and solve. So yeah, let's take a look at how you would do that. You would take the log function that's written there, right up here. Let's move it over here. You would say instead of f of x, you would call that x now. And it would still be log base 3.
Wouldn't it be y?
And this would be a y right here. I'm already switching them. Sorry, I'm doing the extra step ahead of time. And then that would be a minus 2 still. You see what I'm saying?
Yeah.
So yeah, you would take that whole function and switch x and y, where x is, I put a y, where y is, I put an x. And then you'd have to resolve that for y. So to resolve that, I would move the 2 over first. Then I would write this in exponential form, the base being 3, and then switch, make x plus 2 the exponent, and make y plus 4 this, and then solve for y. So there's the actual exponential graph. So this should be down at -4, not -3, I apologize. That should be at -4, the horizontal asymptote. So I can't really slide it down, I don't think can I erase it still? No. So just move this down 1 slot. Okay, that would be a little bit further down. See what I'm saying? Down here. That's where the horizontal asymptote would be. And this would continue to curl a little bit further down. And I know that because this is now my vertical shift. Okay, y equals k is my horizontal asymptote. Yeah, that's how you would find the inverse of that. You should definitely be able to find the inverse of any function. Whether it's logarithmic or exponential, you should be able to find the inverse of any function. Just switch x and y and resolve for y. So then, if you want to, Nick, you asked this question, right? If you want to, you could then continue to adjust the y values and the x values to come up with the y new and the x new values from these transformations. But what would you end up getting, really? You would get the same coordinates, but what would happen? And they would just end up being switched. Okay, the result coordinates would be the same as the result coordinates of this. Just switched.
You asked a specific question where it's like, tell me the inverse of this. Find the inverse of this, like, log.
Sure, and any question could be asked that way, absolutely. Anything could be asked. All right, good question, John. So Clark, to answer your question, because you asked about the half-life formulas, you definitely need to know this formula. Correct? Is that how I wrote it in yours? Because I wrote it different last year. And you also need to know this formula. Whoops. I think we called this capital A. It's the same thing as Y. Okay, those two. Now, do you have to memorize half-life and doubling? You don't have to memorize them because the first formula is what you use. If an object doubles in growth, the rate at which it increases is 100%. So it becomes 1 plus 1, which is 2 of the x. If it half-lifes, the rate of decrease is 50%. 1 minus 0.5 is 0.5 to the x, and that's the half-life formula. So no, you don't have to memorize them. You can just plug in for R to get those values.
Wait, so the formula on the bottom is interest?
When you see the word, there's the word. That's the key word. Okay? The minute you see compound, you know to use the second formula. If you don't hear about compounding, Gus, I would use the first formula always. Even if a problem involved money, I could say, you have $3 and it keeps doubling and doubling. I would use the first formula. If it's compounded interest formula, then you would want to use the second one. Julian?
So every time it's compounded, t is going to be multiplied by n and r is going to be divided by n?
Uh-huh. Absolutely. And that's the only difference in the formulas, right, Julian? You notice that? It's the division by n and the multiplication by n that changes. Or else these formulas are the same actually still, right? Yeah, that's a plus or minus because you can lose rate. But this assumption is that you're making money. You're not losing. You don't have a negative interest rate. Right? There'd be a loss of money. So that's the big change right? Clark?
So I just want to make, like, so compounded quarterly n equals 4, right?
Quarterly is 4, yeah.
So it's just like
Bless you.
compound determines n, like what it's called.
Yep.
Also, similarly, you go over annually, semi-annually again. Oh, God, no.
Semi-annually is twice a year.
So that would be 2, and then biannually would be 1/2, right?
Correct. Once every 2 years. But I already said to you, I'm not going to give you, I'm not going to be a jerk. We had a whole argument about that in class, so I'm not going to make it an English class, right? So it'll be one of those weird things. I mean, you should know your terminology. I shouldn't say that, but I always mixed up bi and semi when I was on it. So,
So the word comes not going to be what's the difference between biand and semi.
that's exactly what we were going to say, yeah?
What is T equal again?
What's what?
What is T equal again?
T is the time elapsed. In this problem, it's years, because the rate is per year. Monthly means 12 times per year. Daily means 365 times per year.
So if it was saying like how much money do I make if I
After-
quarterly after like 2 years?
And it's 2. T is 2.
T is 2.
Yeah. If it says after 60 months, T is not 60, it's 5. 5 years, right?
But if I
I might mess with you and say it's compounded monthly after 60 months. And you might be tempted to put a 16 for T, right?
well if I was doing it by months I couldn't. Like if I had 10 and it was 12, then could I go to the 60?
No.
No?
Again, this is 12 times, what are the units? 12 times per year. 2 times per year. 365 times per year. Everything is per year. So the time has to be in years. Same as the first formula. If I tell you that the amount of bacteria decreases at 20% per day, and I tell you how much bacteria is left after a year, you put in 365 because the units are per day. You follow what I'm saying?
Yeah.
The rate of growth or decrease per time period is indicative of what X should be, or T should be in. So again, it says, I don't know, per hour, and I tell you 2 days have elapsed, the time period is 48 hours, not 2 days. Okay? So X is the time periods at the rate, or with respect to the rate time periods.
So X and T are the same.
Yeah, but remember, T in this formula is always in years. This will never not be in years, every time. This will be in some time period that's a function of the rate. So 20% per day, then X is in units of days. So if the rate is 20% per day, then X has to be in days. It depends on what the rate is given in to know what X should be. Is that clear? Depends on what the rate is given in to know what X should be. I saw the hand pop up.
Yeah, so when you're given an unidentified value in half-life, like if you're given y years pass when the half-life is x and you're given the value for x, you can't solve the entire thing, so you're just going to try to convert it to a log form then, or
Yeah, if you're looking for an exponent, you want to convert to log. You're asking about if there's an unknown in the exponent?
if there's an unknown for how many years have passed, yeah.
Which is the exponent? Yeah, then you would use a log function to solve for that. Absolutely a log function. Whenever the variable is in the exponent, you use logs to solve, always. And remember, if it's a non-calculator question, and your answer is like log base 2 of 7, you leave it like that. You don't have to change it. Okay, feel free to combine stop reading music. In your own 3 o'clock, if you're allowed to take questions, you come by. I'll be here for at least 3:45, 4 o'clock today.
I'm sorry you guys lost baseball, but will office hours now be in the afternoon?
On Wednesday, yeah, because this stuff needs office hours to do it. Sure.
Oh, yeah, boy, I
So yes, 1 minute.
You have to get the outside of the
What's that?
You have to get the outside